Welcome friends, Igor is here, and in this video we will learn how to compute column spaces of matrices. In this lesson we will learn how to describe the column space of a matrix efficiently using only linearly independent columns of a matrix, and we will compute column spaces of all non-singular matrices at once. Let's get started. Let's consider this 5×7 matrix A and its column space. By the definition of the column space, it is a span of the set of the columns of the matrix. Therefore, we need to take the span of a set of 7 vectors of size 5. But we already know that if there are more vectors than size, then this set of vectors is linearly dependent, and therefore we don't need all these vectors to describe the same span. To figure out which vectors we may discard and which vectors we have to keep, we find the reduced row echelon form of this matrix. And we keep those columns in the original matrix that correspond to the pivot columns in the reduced matrix, and we can discard those columns which correspond to non-pivot columns in the reduced matrix. In this case, in the reduced matrix, the pivot columns are columns 1, 3, 4, and 5, and therefore, to describe the column space of the matrix A, all we need are columns 1, 3, 4, and 5 of the original matrix A. Moreover, we also know that this set is a linearly independent spanning set for the column space. So let's summarize this finding. Suppose we have an m×n matrix A and we denote its columns by vectors a1, a2 through an. Let B be the reduced row echelon form of the matrix A, and let's suppose it has R non-zero rows. Then we look at the indices of the pivot columns in the reduced matrix, matrix B, and we take the same columns in the original matrix A. Then this set of columns of the matrix A is linearly independent. Moreover, it spans the column space of the matrix. Notice the use of the special word basis. This word has a very specific meaning, which we'll discover later in the course, but for now keep in mind, basis means linearly independent set that also spans the space. This result allows us to describe column spaces of matrices in the most efficient fashion. For example, let's consider this 3×4 matrix, and we would like to find the best possible description for its column space. For this, we find the reduced row echelon form of this matrix, and we notice that columns 1 and 2 are the pivot columns in the reduced matrix. Therefore, we do not need all 4 columns of the original matrix A to describe the column space. All that it takes is the first 2 columns. Now, let's observe that if you know that a matrix is non-singular, then you automatically know its column space. And conversely, if you know the column space of a matrix, then you might be able to conclude right away that the matrix is non-singular. More precisely, suppose we have a square matrix A of size n, then this matrix is non-singular if and only if its column space is equal to all of Cn. In other words, all possible vectors of size n are in the column space. This is if and only if statement, and therefore there are 2 implications for us to establish. In the forward direction, we are going to assume that the given matrix A of size n is non-singular, and we would like to prove that its column space is all of Cn. Before we proceed, let's understand what it is that we need to prove. We are asked to prove that the column space of A is equal to Cn. So we are asked to prove an equality of certain objects. What are these objects? They are sets. In other words, we need to prove the equality of 2 sets. And we know that to prove the equality of 2 sets, we need to show 2 set inclusions. This argument sets us on the right path to construct the proof. If the matrix A has size n, then it has n rows. This means the columns of the matrix A are column vectors of size n. Therefore, the column space of A is a span of column vectors of size n. Therefore, this span is a subset of Cn. So one set inclusion simply follows from the definition of the column space. And to prove the set equality, what we're missing is the opposite inclusion, that Cn is a subset of the column space of the matrix A. To prove that one set is a subset of another set, we take an arbitrary element of the first set, and we will show that it also belongs to the second set. To this end, let's choose any vector b from Cn. In other words, it is an arbitrary column vector of size n. Our goal is to prove that this vector b belongs to the column space of the matrix A. For this, let's recall that there is a connection between the membership in the column space of a matrix and solutions to linear systems. So, let's construct a linear system with A as the coefficient matrix and B as a vector of constants. Our assumption that A is a non-singular matrix tells us that this linear system has a unique solution. Therefore, in particular, it is consistent. Now, because this linear system is consistent, it means that the vector B belongs to the column space of the matrix A. This shows that every vector from Cn belongs to the column space of the matrix A, and therefore it shows the missing set inclusion. This completes the proof of the fact that two sets are equal. The column space of the matrix A is equal to Cn, the set of all possible vectors of size n. In the opposite direction, let's assume that the column space of the square matrix A is equal to all of Cn. Our goal is to see how this implies that A is a non-singular matrix. Now, here is a trick. Because we assume that every possible column vector is in the column space of A, in particular, it means that all standard unit vectors are in the column space of A. To say that a vector is in a column space of a matrix A is the same as to say that the linear system with A as the coefficient matrix and this vector as a vector of constants is consistent. Therefore, we have n consistent linear systems where the coefficient matrix is always the matrix A and the vector of constants runs through all the possible standard unit vectors. Because all these systems are consistent, I'm going to choose one solution for each system. Let's say the solution of system number I is the vector bi. So I have n solution vectors, which are the column vectors, and I'm going to use these vectors to construct a matrix B. This matrix B is going to be a square matrix of size n. Next, let's see what happens when we multiply the matrix A by this newly constructed matrix B. Let's represent the matrix B using its columns, and I will use the definition of the matrix multiplication. The columns of the product matrix are obtained by multiplying the matrix A by the corresponding columns of the matrix B. However, the vector bi is a solution to a linear system with A as the coefficient matrix and ei as a vector of constants. Therefore, the coefficient matrix A multiplied by the solution vector bi is equal to the vector of constants ei. So, the columns of the product matrix are in fact standard unit vectors. Well, now you see that this matrix is simply the identity matrix. And this computation tells us that the matrix product AB is equal to the identity matrix. Identity matrix is a non-singular matrix, therefore the product of two matrices A and B is a non-singular matrix, and we already proved that the product matrix is non-singular if and only if both terms in the product are non-singular. Therefore, both matrices A and B must be non-singular, and in particular, the matrix A is non-singular. This is exactly what we were trying to prove. Good news! That means our long list of equivalent properties for non-singular matrices grows by one more item. A square matrix of size n is non-singular if and only if its column space is equal to Cn. Notice that this is saying that the column space of the matrix A is as large as possible. If you found this video useful, please give it a like to help others discover this content and subscribe to this channel to see more of these videos. So far, we have concentrated on the columns of the matrix, but matrices also have rows. So in the next video in this series, we will talk about row spaces of matrices. I will see you later.